So first speaker is Dr. Rafal Graczyk. He's research scientist at Interdisciplinary Center for Security, Reliability and Trust at the University of Luxembourg, where he focuses on research related to fault tolerance and security of space infrastructure. Currently, you are working on new technologies enabling safe and cost-efficient exploration and exploitation of space. We touched a little bit this during the keynote. And as well as building a laboratory. I think we'll talk about it a little bit in your talk. Well, it's mainly the focus of it. That will be used for research and education of future space-aware generation of cybersecurity professionals. Right on topic. Rafal, please, the floor is yours.
Good morning. My name is Rafal Graczyk, as you've heard. I would like to share with you our way of thinking about space cybersecurity and the things that we do for actually educating and researching the topic of cybersecurity of space systems. Let me start here with a story. 5 years ago, when I was during the application interview for this post at the laboratory that I am working on, the hiring manager asked me, Rafał, what would you do to secure the satellite for the cybersecurity aspects? And my answer, the answer of the aerospace engineer, was very quick, very sincere, and very incorrect. And I answered, "Sir, with all due respect, it's not possible to hack a satellite." So then I had a little bit more, thoughtful reply afterwards. So in the end, I got the job. But this tells you a little bit about the mindset that aerospace engineers have, and aerospace is my background. So let me introduce you the group that I'm working in. Then I have the privilege and responsibility to share with you the details of how we think about the space systems and the space system cybersecurity. Then I will discuss the need for having such research infrastructure as we build there. And then I will show you what the CritiX Space System Safety and Security Lab is, what are the goals, capabilities, and so on. As for CritiX, we are at the University of Luxembourg. We are dealing with resilience systems and making systems more resilient, including the techniques for hybridizations, including the privacy preserving techniques, and also why are we seeing the slide? Yeah. And also in introducing the verification methods for building the equipment. And we apply this to many technology stacks, the autonomous vehicles, cloud infrastructure, financial technologies, but also space systems. And here's the group. It's Professor Wulp, it's me and a couple of other postdocs and a couple of PhD candidates. This part of group deals with the space systems and safety and security. So for the space system safety is related to faults. So we play with the hardware, we induce faults, we put the systems, the candidates into radiation beams, we see how they fail, we think about the ways of making them better, but also not making them very expensive. As for space system security, we've built a dedicated infrastructure that resembles the space system, the one that you would have in real life, and with that we put the experiments forward. So let's start with the basics. So what is about the space system security? I fall prey to the high ground fallacy, which spilled from the military doctrines about the fact that space assets are considered a high ground. And this spilled into civilian sector, and there was this kind of mindset for many years. Castles are hard to reach and hit, unlike satellites, which are very easy to reach and hit. They are easy to defend. Well, satellites, unlike, they are very challenging to defend. For castles, there are easy ways of fighting back. For satellites, basically no ways of fighting back, for the moment at least. So this it's hard to say why this comparison was there in the first place, but it was there. And is the sanctuary of the space system lost? Well, in first place, probably it was never there. But with classic threats, they were much easier to attribute, and they required sophisticated technology of either kinetic or high energy directed weapons. They were very expensive, and they were effective against standalone targets. So this attack surface was actually very small. Now we are living in a digital world, very networked world, also including the space systems. And now we are facing the cyber threats, which are much harder to attribute, which are exploiting the fact that there's a lot of common technologies used, common interfaces, and that they are shared across many nodes of the network. And they are very inexpensive, and they are very efficient against network environment, meaning that the entry barrier is very low here. And as we know from the history, space assets are very vulnerable. I prepared a couple of examples for you. I mean, the curious example of ROSAT in 1998, that's a satellite that was a scientific satellite managed by NASA for X-ray observations of sun, astrophysical measurements basically, and it died. And there were a couple of explanations what happened. If you know a little bit the space systems, they never made sense. And a couple of years later, actually 10 years later, there was a report by NASA researchers saying that during the time this satellite failed, there was a security breach in the mission control center that was actually managing the satellite, and they attributed the fact the failure of the satellite to the attackers, whoever they were, their cyber attackers, obviously. Interesting thing is that the satellite was based on a bus that was also used in military satellites, so there was a very large incentive really to play with this satellite. Although it's a kind of a national security aspect, so it was never very well documented. But there are other cases very well documented, like the hacking attempts of Landsat and Terra Earth observation satellites, which happened in the northern Atlantic, where the perpetrators they launch attack against those satellites a couple of times, and they made all the steps towards actually gaining full control over the satellite. This has been reported by the Commission of the United States Congress, and we have the documents, that document this event. Another very interesting case are the breaches of JPL networks, also including deep space networks, so the network connecting ground stations communicating with the probes exploring space system. There were hundreds of megabytes of this very sensitive data stolen during those breaches, and the network that is used for the communicating with those probes has not been operational in a regular way for many months after. And this was just unsolicited Raspberry Pi, that was connected to the JPL network that was distributing the Wi-Fi signal over the fence. Another case is like the mayhem at the TV5 Monde, where the attackers first got inside the network of the TV station. They were there in months, during the several months, mapping the operation of the TV broadcasting system, finding out what are the sensitive nodes and what they have to do to actually disable the whole broadcasting system. And they prepared even a special dedicated software to launch the attack. And during the attack, they uploaded the firmware, which really destroyed the hardware, the transceivers, which made the station unoperational for at least a couple of hours. GPS spoofing, this is something which is happening very often these days. Those are the famous GPS crop circles that we see, that here the data from AIS system, the maritime traffic monitoring system, which provides the coordinates of the ships. So we see that they are circling the spoofing station instead of sailing over the river nearby. Classic example. And it took us a while to really realize that there's a problem and do some actions. This list shows all the attacks that I have found out that they were there in the history, that were somehow documented, that I could get to some kind of information, reliable information about them. In red line denotes the 2001 talk of Donald Rumsfeld about the risk of space Pearl Harbor. Then we see the attacks that that I've shown you when they were, and it's just like 20 years later. There's kind of documents, standards, and approaches that are enforced on space systems, operators, and vendors to make sure that cybersecurity is there, at least addressed somehow. So this allows us to map like what are the generic space infrastructure attack vectors. Space infrastructure is very complex. We know that there are the space segment, the ground segment, and the supply chains. Let me just walk you through all of those segments. For the supply chain, I analyzed all the vectors regarding the confidentiality, integrity, and availability. For confidentiality is the design or specification. Theft, this is very important. Well, hackers need to know exactly what they are addressing, what kind of equipment is there, what is the topology, what are the specifications of the equipment. Integrity is modification of those. It could even mean modification of the test specification, turning your qualification test into a destructive test if the setup of the machine testing your equipment is somehow affected. As for availability, is the deletion of all those or disrupting the supply chains and or disrupting the availability of a test facility. For ground segment, for confidentiality, it's typical listening to do something that you shouldn't listen to. So eavesdropping and tracking of the ground stations, of the satellite, and eavesdropping on mission control. And in terms of space traffic management, also tracking the objects which you shouldn't track. For integrity, it's masquerading, message replays, modification of commands or telemetry, or man-in-the-middle type of attack against ephemerid distribution systems. For availability, it's the denial of those, so denial of service, denial jamming, facility and unavailability, or deleting the objects tracked by the STM systems. For launch segment, well, disclosing the payload which is on the rocket, tracking the orbit it is injected into. For integrity is perhaps trajectory modification or GNSS meconing or spoofing, although this would probably be compensated by inertial navigation systems. As for availability is the activation of the flight termination system, so blowing up your rocket or disabling the separation at the kick stage. So several attacks possible. For space segment, we're having for confidentiality unauthorized access, eavesdropping, and also user terminal tracking. For integrity, we are having the unauthorized access again and fault induction. So we are now trying to system behave well, a little bit different than expected. Masquerading for relays, and data modification or spoofing for user terminal. In terms of availability, it's jamming, blinding for satellites, and failure induction. So we have successfully induced fault that turned into the failure that disabled part of the system, and denial of service, jamming, and so on. This enables us to build the pyramid of a space system attack. We build on a knowledge of how the system works. Then we have to have access to the means of communication. And then we have to be able to track and monitor what is happening out there with a space system. And finally, we can launch an attack against the space system. Well, so we know, if we know this, we need to, well, first educate people, the red teams, how to attack, what skills are required. For the blue teams, how they should monitor the assets to find out there's something wrong going on, and how to ensure that the system will maintain availability. And in general, we need to raise awareness. As for experimentation on such infrastructure, we need to have a means to search for vulnerabilities, experiment with the hardware and the software, especially that there's a lot of standard blocks. And we need to have a means to develop resilience to test out our solutions, whether they make the systems more resilient or not. And here comes the CritiX lab. We directly mapped our space system attack pyramid into the infrastructure that we built. So first on the knowledge part of the system, we decided we need to go with something very standard. So those are the CubeSats, the CubeSat standards, which are very well defined, very common nowadays, and very easily accessible. They are open source. It also provides a lot of specification details on how to test your systems. And there's a lot of open source software and also hardware that you can play with and that you can experiment and that you don't have to develop everything from scratch. As for the access of means of communication, it's simply the ground station that we have built there that enables us to communicate with a satellite. But also we have another ground stations, the rogue one for the eavesdropping and extremely rogue one for interfering with your signal, with the communication, so with the ability to transmit signals. And in the end, we also want to know what is happening on the satellite side. So we need to have insight into the onboard bus. And this is the wired connection that we also have there in our infrastructure. Then we have tracking and monitoring, which enables us to simulate the fact that the satellite is not always there available for us. So we are able to propagate the orbits using some open source software like GMAT, for example, in this case, used for modeling missions. And we need to have ability to monitor radio spectrum and to see how the attempts of attacks are visible in radio spectrum. What can we do about it? How soon we can realize that there's an attack going on, and so on. And in the end, we have the pinnacle, the attack on a space system, which requires us to have a satellite. And this is a satellite that we have. It's a flat sat, so it's a flat satellite, but it contains the components, the subsystems that are basically equivalent one-to-one of a flight units that you would have in your small satellite orbiting the Earth. And we have power distribution unit, one that switches on and off all the devices in the system. We have the onboard computer that have a scheduler and that have capability to generate telemetry and answer to the telecommands and manage the whole satellite bus. We obviously have also the means to communicate with this satellite by telemetry and telecommand unit using standard communication interfaces, radio interfaces like HDLC or AX25. And in the end, we have another cherry on top, which is attitude determination control system together with an actuator, which is a reaction wheel. Which, it's not necessary to stabilize this because it's already sitting on a table, but if you want to have a very nice presentation of the success of your attack, you may want to show to everyone that, well, you have just now either stopped reaction wheel and then start to spin the satellite, or you just spin the reaction wheel out of the control, making it even worse. So with that, I think that the future of space system security depends heavily on teamwork, and for that I would like you to treat this presentation as an invitation for a collaboration on joint research, if you like, or if you're industry, we might form a partnership to dive a little bit deeper into your needs or what type of systems you are dealing with. It may end up in some kind of consultancy, if you will. If you are a PhD student and you are defending your thesis and you would like to have a postdoc, it's also possible to do this with us on this infrastructure and play a little bit more. Feel free to contact me on those emails or on LinkedIn. And with that, I would like to thank you for your attention, and I think it's the time for the questions.
Thank you, Rafal. I don't see any question apart from having the slides available for the public and registrant. I don't know what's planned by the organizers. We don't know yet about the slides. Maybe you should just, if you want more information, just contact Rafal and you can exchange with him.
I have a booth out there in the innovation corner, so it's relatively easy to find me. I can also show you again the means for contact, if you like. I'm going to stay 2 days here, so there will be a chance to discuss if you like.
Do we have any question? Maybe another one?
How easy is it to differentiate purposeful malleolous attack from natural events or disruptions?
Well, it depends on what type of attack. If you are you asking about the radio spectrum, or well, that's why we are building the infrastructure which is called safety and security, because for us it's two sides of the same coin. So it's not really that different. It's just the different statistic is behind that, I would say.
Still a few seconds. No more questions? I have one actually. What's your position? Well, we've seen the announcement made by CYSAT with Thales that they act and they will have a live demo tomorrow on upset hacking. What's your limitation when working in laboratory versus working on a live system? We've used a lot of simulation because it's tricky to do any analysis, and it's more limited to do analysis for flying space vehicle.
Yeah, if we want to address, let's say, functional aspect of the cyber attack, that's already perfect. That's very good resemblance. If we want to go more into the physical details of the fact that the communication has some latency and some issues, at the University of Luxembourg, the other groups, they have a very sophisticated satellite communication link simulators, so we can make it really, really realistic, because it's those simulators are used for validation of industrial grade satellite links.
Okay, thank you.
Thank you.
Time's up. Thanks again, Rafal.